You can start now.
The agenda of this 1.5 hour session is to make you understand what is static timing analysis, why is it required in VLSI backend, in VLSI physical design, and then to start with static timing analysis, what are the basic terminologies we need to know, and which tool we are going to use. And I have also included a sample script in the last slide. All right, for you to understand how STA is done by the tool. It could be PrimeTime or Tempest, whichever tool we are using. The procedure is the same, just that the tool differs. That's all. So I have included a sample script. So this is how our workshop will go for today. You can stop me whenever you're having any doubts. All right. Now, first of all, static timing analysis means that we are going to design an IC. Okay. And for this IC, there will be multiple types of constraints. Constraints means the conditions or the rules which the IC has to follow, like the area, power, memory, number of input ports, number of output ports. So, like this, there are many conditions. We call it constraints. And there are multiple types of constraints, which we call them as timing constraints, area constraints, and power constraints. Now, timing constraints means it talks about the time period of the clock or the frequency on which our IC is going to work. Now, if our IC is expected to work in 1 gigahertz frequency, then it means what? The clock period must be 1 nanosecond. And when we are talking about clock period, it applies to the sequential elements which we are using in our IC. Sequential elements means the flip-flops. So we all know flip-flops are memory storage devices, just 1-bit memory storage devices. They're going to take the data in and push it out at the respective clock period, respective clock pulse. This is the work of the flip-flop. Now, this is how our entire IC is going to work because we are having millions of flip-flops inside our IC. Because we are going to integrate multiple applications in a single IC. Now, if we take an IC which we are going to use for our phone, it does multiple applications. We are able to load many types of applications on our smartphone. Why is it possible? Because our IC is able to accommodate so many millions of flip-flops, which is going to perform those many applications. So when one small simple IC, which is very, very small, is going to work on those many a number of applications, we need to check if it is going to do it the right way. That is what is called as static timing analysis. We are going to analyze if the IC which we are going to build is going to work properly according to the clock period which we are assigning for the IC. All right. And when coming to clock period, it is not that our IC is going to have only one clock. There will be multiple clocks. 3 source clocks we can have, 4 generated clocks we can have, depending upon the um, requirement of the architecture of the IC, the clock period will differ. Now, for example, if you have 5 modules in the entire architecture of the IC, 2 modules require 1 nanosecond. Another two modules require only 0.8 nanosecond. The next one pending module requires 0.5 nanoseconds. So what do you need in this case? You need 3 different clocks to make all the flip-flops work in all of these modules. And all of these must be in synchronous with each other. That is important. So if 2 flip-flops are in sync with each other, we should make sure that the data is transmitted from one flip-flop to another flip-flop within that mentioned clock period. So likewise, we need to have a coherent function in our IC. That is why we are doing this static timing analysis for our IC. Now, to do this static timing analysis, we need to understand some basic terminologies. All right. Static timing analysis is a method of validating the timing performance of a design by checking all possible paths for timing violation. possible paths means data paths. The components of our IC are nothing but flip-flops, combinational elements, and all of these sequential and combinational elements are connected using nets, using metal wires. What is going to happen basically? Data transmission is going to happen. If there is an inverter and then the output of the inverter is connected to a flip-flop, the data must transmit from the inverter to the flip-flop. And then from that flip-flop, if there is one more flip-flop connected, the data must be transmitted to the next flip-flop within the mentioned clock period. So this transfer of data signals must happen without tampering the clock period which we have assigned. So to check that only, we are going to do static timing analysis. And here by checking all possible paths for timing violation means the possible data paths. All right. Now these possible paths are called as timing paths. And these timing paths can be divided into 4 categories. So we have 4 different types of timing paths. So the very first topic which you have to cover in static timing analysis is the different types of timing paths. Am I clear? Any doubt so far?
No.
All right.
No, ma'am.
Okay. So we have 4 different types of timing paths. Now these 4 different types of, we are categorizing these 4 different types of paths based on the start point from where the data is emerging. Now here if you see path 1. So this path 1 starts from this point A. So this is a symbol for the input port. All right. Now from this input port, where is it ending? To the D pin of the flip-flop. So if a data path is starting from an input port, it could be any input port. So from an input port to a flip-flop, it is called as in-to-reg path. All right, input to register. That's what we call it as in-to-reg path. So that is the first category. Second category is path 2. So this path 2 starts from the clock pin of this flip-flop and it ends in the D pin of the next flip-flop. Why we are showing that the data path is starting from the clock is because only when the clock is enabled, the D pin is going to tap the data to the output. So the controlling character in the flip-flop is a clock rather than the D pin. So that's why it is mentioned that from the clock pin to the D pin of the next flip-flop. So all the timing paths which start from a flip-flop or which start from a register and end in a register are called as Reg-to-reg paths. That is the second category. Third category is from a register to a output port. So this is an output port here. So the symbol for the input ports and output ports are likewise. So from a flip-flop or from a register to an output port is the third category. That is called as Reg-to-out path. And then the final category is from input port to the output port. So there will not be any flip-flops in between. No sequential elements will be in between an input and output port. There could be combinational elements. So this logic, whatever you see here are combinational elements. Combinational elements means what? Our logic gates, AND gates, OR gates, buffers, inverters, all of these comes under the combinational logic category. All right. So we have 4 different types of paths. I will just mention it here. In-to-reg, reg-to-reg, reg-to-out, in-to. So these are the 4 types of timing paths. Now the very first concept in STA is to first categorize the timing paths. All right, this categorization we will do in the stage of synthesis itself. So there itself we will do this categorization. Now, why we are doing this categorization is because the timing requirements for each of these paths will differ. Now why? Because now reg to reg means these two registers will be present inside one block. Into reg means the input port. So this input port carries the data from a flip-flop which is outside this block. So let us assume there are two blocks. So from one block, in one block there is a register, and from that register, this input port is carrying the output of that register and pushing it to the another block. So this input port is going to carry the data from one more block of the IC. So when the data is coming from one more block, the timing characteristics for these datas will be different from the reg to reg datas. So that is why we are doing this categorization. All of the other, like what are the different categorizations, we'll see in the upcoming slides. So for now, these are the four different types of timing parts. First in first point in static timing analysis is doing this categorization where we categorize all of the different timing parts. Okay, next is, so yeah, here I have mentioned path 1 starts from input port to the data input of a sequential element. Path 2 is from the clock pin of a sequential element to the data input of a sequential element. Path 3 is clock pin to output port. Path 4 is input to output port. Okay. So this is the first concept which we have to learn in static timing analysis. Next is some characteristics of the sequential elements which we have to learn. So to this part, I'll come later. First, I will explain this timing arcs, cell arc, combinational sequential arcs, and then these concepts I'll cover, and then I'll come to this. Only then it will make sense. First is timing arc. The timing arc means a path from each input to each output of a cell. Every combinational logic has, let me put it in slideshow mode. Is the screen visible in slideshow mode?
Yes, it is visible.
Every combinational logic has multiple timing arcs. Basically, it represents how much time one input takes to reach up to the output. So now let's assume there is an AND gate. An AND gate has two inputs, A, B, and one output. A, B, and this is Y. So what is the timing arc? A path from each input to the output. So if we are sending a data from the input port A to Y, then we draw a line like this, and these timing arcs are just virtual representations for us to understand the timing concepts. So these are not like real elements. These are just virtual arcs which we do for our understanding and to do the STA easily. So if there is a timing arc from A to Y, it means that the data is sent from A and it reaches Y. If there is a timing arc from B to Y, then it means what? The data is sent from B and it is obtained at Y. So this is called as a timing arc. Now this timing arc can be divided into combinational arcs and sequential arcs. Combinational arcs means any timing arc which is drawn for combinational elements like logic gates, buffers, or inverters. They are called as combinational arcs. Sequential arcs means what? You have a flip-flop. And what are the ports, input and output ports of a flip-flop? There is a D pin, there's a clock pin, and there's a Q pin. And for a sequential element, we will draw the timing arc from the clock pin to the Q pin. Why? Only when the clock is enabled, the data is transferred from D to Q.
So since clock is the controlling element in the flip-flop, we will draw the timing arc from the clock to Q. So if we are going to consider a sequential element, you have to remember that from the clock pin to the Q pin. But for combinational elements, we don't have any controlling element as such. We don't have any clock signals to enable the combinational elements. So we will draw the timing arcs right away from the input to the output ports. So this is all about combinational arcs and sequential arcs. Okay, I'll move to the next slide. Next is unateness. Again, unateness is like a concept which is going to explain how the output is responding to the input in a logic gate. So each timing arc has a timing sense. So unateness is also called as timing sense. That means how the output changes for different types of transition on the input is called as unateness. Now in this unateness, there are three categories. One is positive unateness, negative unate, and non-unate. Now positive unate means if a rising transition on the input gives the output to rise and falling transition on the input gives the output to fall, that is, there is no change in transition of input and output, then the timing arc is called as positive unate. So positive unate means in the input side, there is a rising transition, 0 to 1. So if there is a rise transition in the input side, on the output side also, you experience the same transition. If you are giving if a rise transition is occurring in the input side, if the same rise transition will occur at the output side. If there is a fall transition in the input side, a fall transition will occur on the output side. If you are experiencing such kind of a behavior in your combinational cells, it is called as positive unate. And examples of positive units are buffers, AND gate, and OR gate. Now, if we see the truth table for these gates, it will be even more understandable. So buffer means what? It is only going to strengthen the signal. It is not going to make any other changes. So whatever we are going to send as input is only going to get amplified. Nothing else is going to change. The transition is not going to change. If you are going to send 0, the same 0 only we will be seeing at the output of a buffer also. So that is why it is an example of a positive unit. Now coming to negative unit, if a rising transition on the input gives the output to fall and the falling transition on the input gives the output to rise, it is a negative unit. So negative unit is just the opposite of a positive unit. In the input side, you're seeing a rise transition. Then the output will give a fall transition, an opposite. So if you're making the input to change from 0 to 1 in the input side, the output will be 0. So 1 to 0, which means what you're seeing a fall transition. So if your output is showing such kind of a behavior, it is called as negative unit. And examples for negative unit are inverters, NAND, and OR gates. These are the examples of negative units. Non-unit means you will not be able to predict the character. So for certain gates, we will not be able to make a prediction how the output will differ based on the inputs transition. So those are called as non-unit gates. So XOR and XNOR are non-unit gates. All right, so this is all about unateness. Next is very important concepts of static timing analysis, which is setup time and hold time. I hope everybody is aware about setup and hold. Can anybody explain what is setup and hold time? What is setup time? So this setup time and hold time are constraints which we set for the flip-flops. Why? Because we need to know that the data which we are going to send is going to be stable at the output. So if you're sending 1 at the D pin, the same 1 must appear at the Q pin. If the flip-flop is tampering with the input and instead of 1, if it is sending 0, then the entire objective is missed there. Because the data, the work of the flip-flop is to transfer data from the D to Q, and also it should not change the quality or the value of the input. So to check these, we are having two concepts called as setup time and hold time. Now, what is setup time? Setup time is the minimum amount of time for which the input data must be held stable or steady before the occurrence of the clock cycle. So this is the data signal, and this is the clock. So the clock, rising edge of the clock is here. At the rising edge of the clock, what will happen? The D input will be taken inside to the flip-flop and it will be transferred at the Q pin. So this requirement, sometime before the clock period itself, the data must be stable. If there is going to be any change in the data at this time, then we will be facing some metastability issues or stability issues at the flip-flop with respect to that particular input. That is called as setup time. So the data must be stable for some time before the active edge of the clock. That is called as setup time. Next is hold time. What is hold time? The
Excuse me,
data
ma'am.
must, yes.
Uh, Sorry to interrupt you. I have a question regarding the setup time. So,
Mhm.
is it supposed to be like a physical property of the register, or is it a constraint that we assign to the register with setup
It
time?
is it is a constraint that we assign to the register. We will
Okay,
mention the setup time and hold time of the flip-flops in the libraries.
okay, but how does in like a designer know how much value to assign it, or how much constraint value to?
Mm. So every flip-flop will be when every flip-flop is manufactured, they will have a set of designers who will do the simulations on these flip-flops. So they will decide for what amount of time this data must be stable for that particular flip-flop. So they will send data with multiple transition times. So when we are giving an input like 0 to 1 or 1 to 0, the transition time for that flip-flop will be considered. Okay, like 10 ps or 20 ps, that much amount of time must be taken for the data to transition from its previous state to the present state. So based on that, for how much time before the transition is going to occur, that flip-flop will be able to handle the particular data with that respective transition time. So they will do simulations with multiple transition times. So they will send datas with multiple transition times like 20 ps or 30 ps. And when the data is finally arrived at the Q pin, if the desired data is arrived with the setup time which they have mentioned, and if it is repeatedly happening at the same time. For example, if they have set setup time as 100 ps, with 100 ps, multiple transition times of data will be sent. So 100 ps will be the setup time which they will start with 100 ps. They will start with one approximate value, and setting the setup time as 100 ps, multiple data transition times, they will send the data to the flip-flop. And when the output is observed at the end of the flip-flop, if the data is hampered or not, if it is deviating from the original signal, so if it is one, instead of 1, it is not arriving at output y with the same 1 which is sent, then they will change the setup time. So if it is going to not change, and if at least 90 to 95% of accuracy is accurate data is obtained at the output Y, then they will fix that value as a setup time for that particular flip-flop. And also inside a flip-flop, we have transmission gates and inverters. So these transmission gates and inverters only make the internal circuitry of the flip-flop. So this setup time will be dependent upon how these inverters and transmission gates are going to transfer the data from their input to their respective output. So based on all of these values, simulations will be done, and then finally a setup time will be fixed for a particular flip-flop. Is it clear, or you're still having any doubts in this?
Got it, ma'am.
All right. So next is hold time. Hold time in STA means the minimum amount of time of required time for which the input data must be held steady or stable after the occurrence of the clock cycle event. So now in the hold time scenario, the data has already entered the flip-flop. Now the data has already entered the flip-flop, but it has still not reached the Q pin. Now at the second clock pulse, now in the first rising edge, the data will enter the flip-flop. At the second rising edge, two events will occur. What are the two events? The data which entered the flip-flop must be sent to the Q pin, and the new data will arrive at the data pin, at the D pin of the flip-flop. So now if this new data which is going to enter this flip-flop is arriving too soon, then it will hinder the data which is already inside the flip-flop. So we should make sure that this does not happen. So that is why we have hold time, and this hold time in static timing analysis is the minimum amount of required time for which the input data must be held steady or stable after the occurrence of the clock cycle event. So here, after this rising edge, the data has entered the flip-flop. Once the data has entered the flip-flop, so at this point, the data has entered the flip-flop. Now, what the flip-flop has to do? From D, it has to transfer it to Q. To do that transfer, it will take some time, right? So let us say it is taking this much amount of time. So let us assume this is 0 nanoseconds. Here it is 5 nanoseconds. So this much amount of time the flip-flop is taking to transfer D to Q. So let us consider this as 1 nanosecond. So the flip-flop is taking 1 nanosecond to process the input. So for this 1 nanosecond, the data must be stable. It must not deviate from its original value. So after this 1 nanosecond, what will happen? The data will move from the D pin to the Q pin. So after the data has moved from D to Q, there is no need for us to check for the stability of the of the data, because the data has already reached the output of the flip-flop. So when the data must be stable, the data must be stable for some time when the flip-flop is processing that data. So that is called as hold time. Once the data must be stable before reaching the flip-flop, and after reaching the flip-flop also it has to be stable, because the flip-flop needs some time to process that input and send it to the output. So for that process time, the data must be stable, because the internal circuitry of the flip-flop also must not change change the input value. It could be anything. Even if it is going to be 0, it has to maintain it to 0, maintain it the same 0 value. If it is 1, it has to maintain it as 1. So when the flip-flop is doing the process of transferring this D to Q, also the data must be stable inside the flip-flop. So to check that only we have this hold time. That is why hold time is checked after the data has entered, which means after the rising edge, for this much amount of time, the data must be stable. That is called as hold time. Any doubts in hold time?
Just a question here, like, so the hold, for example, this we will have some violations, right? So if there is some hold time violation, it is also ensuring that setup time is also violation is there. Is that a correct understanding?
No, it doesn't mean so. It doesn't mean that if there is a hold time violation, there is a setup violation. No, it is not like that. If you see the formulas for setup and hold violations, there will be a slight difference. So in setup, for setup time calculation, we will include the clock period. For hold time violation, we will not include the clock period. So it is not like if a violation has happened, a setup violation will also happen. It is not like that. They are exclusive. It can happen, but it is not mandatory. It is not logical to say that if there is a hold, there will be a setup also.
Okay.
Possibilities are there, but it is not for all the scenarios.
Okay, because we were discussing like that, like before the data is being stable, the one more input is coming, like coming in, right? So
Hmm.
to the input pin, so we have a setup violation where the data has to be in a stable state, right?
Hmm.
So if the data is in the stable state,
Hmm.
so we will not be getting that like it's like the input is not hurrying up, right? So that's the confusion here.
Yeah. Now, yes, for now, I'm able to understand what you're telling, but for this setup time and hold time, we will be calculating we will be calculating this with two different paths. So we call it as clock path and data path, or we can say it as required time path and arrival time path. So when we are considering these parameters, maybe in the upcoming slides you will get it cleared. So
Okay, okay, no
yes,
problem.
when this slide is explained, I will explain
Okay,
whatever your doubt is. I'll explain.
okay. So
Okay.
we can for now it's like it's not compulsory. It might happen,
Yes.
but it's not. Okay.
Yes, it might happen, but it is not the same for all the scenarios.
Sure, sure. Thanks.
So that's all about setup and hold time. Next is clock skew. Clock skew in STA is a time parameter that occurs when the difference in arrival time of the clock to two or more flip-flops are in the same clock domain. So now you have a flip-flop. There is one more flip-flop here. It is enabled by the same clock. So there is a clock port. From this clock port, clock signal is arriving at this flip-flop, and the clock signal is arriving at this flip-flop. Now, any signal to transfer from a start point to an end point, it will take some time. In generic, we will call it as propagation delay. But with respect to clock, we will call it as arrival time of the clock. So if this clock signal is taking 1 nanosecond to reach from this point to this clock pin of the flip-flop, we say that as arrival time of the clock for this flip-flop is 1 nanosecond. And if this path is taking 2 ns, we say arrival time for the clock with respect to this flip-flop is 2 nanosecond. That is the terminology which we use. So this is the arrival times. Now what is skew? The difference of these arrival times. 2 nanosecond minus 1 nanosecond is the clock skew. The difference in the arrival times of any two respective flip-flops. Now this is not only for two consecutive flip-flops. It could be for any different types of flip-flops. So if it is going to be for two consecutive flip-flops, we call it as local skew. If it is going to be for flip-flops in an entire block, we call it as global skew. In an entire block means this is an entire block of an IC and there could be millions of flip-flops in this. Now, if we are going to say local skew, it is the time difference between two consecutive flip-flops. Global skew means the flip-flop which is very near to the clock port and the flip-flop which is very far away from the clock port. So if this flip-flop is taking 10 PS arrival time, this clock will definitely take more time because it is very far away from the clock port. So the clock net which we are using to connect this will also be more. The length of the clock net will be more. So as the length of the clock net increases, the delay will also increase. So if this flip-flop is taking 10 PS, this flip-flop could take 100 PS to transmit the clock signal. So 100 minus 10, 90 PS is the global skew. Okay, so that is the difference between local skew and global skew. Local skew means difference in the arrival time between consecutive flip-flops. Global skew means difference in the arrival time between the flip-flops in the entire block of an IC, which is one which is very close to the clock port and the one which is very far away from the clock port. So that is called global skew. Next is clock to queue delay. And this is one more important parameter for STA. We will see this in the setup and hold time formulas. Clock to queue delay in static timing analysis is the time delay difference between the clock pin of a flip-flop to the output pin or after the clock trigger of a flip-flop, the time taken by the input data signal to reach the flip-flop. Let me erase all of this. Now in a flip-flop, the controlling element is the clock, right? This is the D and Q. So when the clock at the rising edge of the clock, data at present at D will be tapped to Q. So since clock is the controlling element, we will draw it from the clock, not from D. So the time taken for the data to transfer to Q from D at the rising edge of the clock is called as clock to Q delay. Basically the time taken by a data to move from the input port to the output port. That is called as clock to Q delay. Why we call it as clock to Q delay? Because the clock only is going to control at which edge the data must be transferred from the D pin. So that is why we call it as clock to Q delay. All right. So next is
One question.
yeah.
So this STA is applicable to only synchronous circuits, or can be applied to asynchronous as well, because we were
No,
dealing with the
we don't do
sync.
STA for asynchronous. Only for synchronous clocks we will do this STA.
Okay.
Yes. See, there are 3 clocks. We will do STA for all the timing paths in the
Okay.
block. But if 2 clocks are synchronous with each other, we will do the STA for those 2 clocks. If there are two other clocks which are like assume you have 4 clocks. Clock 1 and clock 2 are in synchronous with each other. Clock 3 and clock 4 are synchronous with each other. So we will do STA for clock 1 and clock 2, clock 3 and clock 4, not for clock 1 and clock 3. You got
Okay.
the point?
Yeah.
There is no need for us to do STA for asynchronous clocks, right? Because they're not going to get involved in the timing paths.
Yeah, sure, understood.
Okay. You have a flip-flop. This is the launch flip-flop where the data is going to be launched, and this is the capture flip-flop. Okay. This is launch and this is capture. There is one clock which is driving this launch flip-flop. There is one more clock driving the capture flip-flop. Okay. Now there is one other timing path here. There is one launch flip-flop and capture flip-flop. This clock is going to enable this launch. There is one more third clock which is going to enable this capture. So it will make sense for me to do STA for this timing path. If I'm going to do STA for this timing path, which two clocks I will consider? This clock and this clock. When I'm going to do timing analysis for this timing path, there is no need for me to consider this clock, right? Because this is nowhere involved in this timing path. You got the point?
Oh, yes, understood. Yeah.
When I'm going to do a timing analysis for this timing path, I will consider this clock, the second clock, and third clock. Now, in this case, there is no need for me to check for the clock one at all because it is no way involved in my timing path. All right.
Yeah, got it.
Ma'am, I have a general question regarding
Yes.
clock. So, when you say that the clocks are synchronized, that means they are in the same phase, but the frequencies could be different.
Yes, it could be.
Okay, and so for a particular design, they use one common clock and they derive other clocks from it for different modules?
Yes, it
Or
is possible.
could we?
That is,
Yeah.
yes, there will be a source clock and there could be generated clocks from that also. And there could be two other clocks which are asynchronous with that clocks also. So this totally depends upon the architecture of the IC. So how the RTL, so if there are 5 modules and 2 modules require synchronous clocks, then for those 2 modules, we will create one source clock and then a generated clock we will create. For the third module, we will create one more totally new clock, which is asynchronous with the other 2 clocks. Depends upon the requirement of our design.
And each asynchronous clock will have its own static timing analysis. Is it that way or?
See, static timing analysis we are going to do for the timing paths, not for the clocks. All right.
Okay.
Okay. See here,
So
we are
if,
going to do
yeah,
STA for the timing paths, not for the clocks. These timing paths are enabled by the clocks.
right.
So we are going to check now if this path 2 is enabled by a clock, if this is 1 nanosecond time period, what does it mean? The data which is going to be sent from this flip-flop to this flip-flop must reach within 1 nanosecond, not more than 1 nanosecond. That is my agenda. In static timing analysis, I'm going to check if the launch flip-flop is sending the data and the capture flip-flop is capturing the same data within 1 nanosecond or not. This is what I'm going to do in STA. So STA is focused on the timing parts and not on the clocks.
Right. Sorry, my question was so for the data path with a synchronous clock, that will have a different timing analysis. So for each data path, which a different clock or a synchronous clock will have a different timing analysis.
Yes.
Okay.
See, the timing analysis procedure is the same. Only the clocks which are related to each of the timing paths will differ.
Got it.
Okay. Okay, so next we will move to these concepts. Clock path, clock gating path, asynchronous, false, and multi-cycle paths. So what is a clock path? A path from a clock input port or a cell pin through one or more buffers or inverters to the clock pin of a sequential element for data setup and hold checks. Basically, the path the clock signal follows is a clock path. So the clock signal is going to emerge from a clock port. So there will be a PLL. From the PLL, there will be a clock port. From the clock port to the clock pin of the flip-flop. So this is the path this clock signal is going to take. So hence it is called as a clock path. Next is called as clock gating path. A path from the input port to a clock gating element for clock gating setup and hold checks. Now, is everybody aware of clock gating concept? If not, I will explain first what is clock gating.
No, ma'am.
All right, give me a minute, I'll be back. Now, clock gating is a concept which we follow to reduce the clock power. Now, since clock is a constantly switching signal, the dynamic power incurred in a clock will be more. So to reduce the dynamic power, we will use something called as clock gating cells. So what this clock gating cells will basically do is, whenever clock signal is not required for a set of flip-flops at a particular time, for a particular time, it will turn off this clock. And it will turn on the clock only when those flip-flops require the clock. Now, for example, you have 20 flip-flops in your design, and for first 2 nanoseconds, the first 10 flip-flops do not require a clock signal. After 2.1 nanosecond only, these flip-flops require a clock. So for the first 2 nanoseconds, there is no need for us to transmit the clock signal from the clock port to the clock pins of these 10 flip-flops, right? So for the first 2 nanoseconds, we will turn off this clock signal. So to do that, we use some cells called as integrated clock gating cells. We call them ICG cells. So these ICG cells will gate the clock, meaning they will just turn off the clock supply to the flip-flops when they do not require. So by this, we are saving the dynamic power incurred by the clock. So those clocks which go through these ICG cells are called as clock gating paths. When a clock signal is going through an ICG cell, we call it as a clock gating path. Next is asynchronous path. A path from an input port to an asynchronous set or a clear pin or a sequential element for recovery and removal checks. We call it as asynchronous paths. So in a flip-flop, what are the asynchronous inputs? Reset, set, enable. These are the asynchronous pins. So these pins do not require clock. Hence, they're called as asynchronous. So any path which goes to these pins are called as asynchronous paths. Next is false path, a path that is never sensitized due to logic configuration, expected data sequence, or operating mode. False path means a path for which timing analysis is not required. For this example, I will give one example. So this is a mux, inputs and output. and this is the select pin. So this select pin of this mux, any nets which are connected to these select pins do not require timing analysis, which means what? Basically, clock signals are not required for the select pins of the multiplexer, because the work of a select pin is only to tap the respective input to the output. And these select pins do not require a clock signal, and there is no need for us to do a timing analysis for these select pins. So these pins are called as, any paths which are connected to these select pins are called as false paths, because for these false paths, we do not require timing analysis. We have to do timing analysis only for data carrying paths, not for any other paths, basically. So that is why the paths which do not carry data, we will call them as false paths. Next is multi-cycle path, a path designed to take more than one clock cycle from the launch to capture. Now here, if there is a flip-flop, there's one more flip-flop. So this is a Reg-to-reg path, and there is some combinational logic in between. Some gates and inverters and buffers are present. Now, if there is a, if the combinational logic present in this path is heavy, heavy means there are more gates. So if there are some 50 gates and 20 buffers and 10 inverters, then we call it as a logic heavy data path. So if the logic is more, then the data will not be able to be sent to the capture flip-flop in one clock cycle itself. So if one clock cycle is 1 nanosecond, this path will not be able to be send data within this 1 nanosecond, because from this launch, it has to travel through all of those 50 gates and then finally reach the capture flip-flop. So 1 nanosecond might not be sufficient for this data. So instead of assigning one clock cycle, we will assign 2 or 3 clock cycles depending upon the requirement of the flip-flop, the requirement of the data path. So for this data path alone, I will assign 2 clock cycles or 3 clock cycles. So then what? If I'm assigning 3 clock cycles, then 3 nanoseconds will be the time period for this path alone. So when the data is launched from this flip-flop, it can take 3 nanoseconds to travel from here and reach the capture flip-flop. And these paths are called as multi-cycle paths because they require more than one clock cycle. And we will not have give this for all the timing paths, only for timing paths which are having very high requirements like this, more combinational logic in between. So those paths are called as multi-cycle paths. And for other paths, only one clock cycle, the standard one clock cycle only will be the time given for the data to be transferred from the launch to the capture. All right. Next is minimum or maximum delay path, a path that must meet a delay constraint that you explicitly specify as a time value. Now, just like how this multi-cycle path is an exception, we have two other exceptions called as minimum or maximum delay path. Now, these paths require 3 nanoseconds. There could be some paths which require 2.5 nanoseconds or 4.5 nanoseconds. So there could be very exceptional critical paths like this. So those paths alone, we will be calling them as maximum delay paths, or minimum delay paths means some paths will not have very much combinational logic in between. So they might require only 0.1 ns time to transfer data from the launch to capture. So they don't even want one full clock cycle. So there is no need for us to waste our clock period there. So those paths alone, we will set them as minimum delay path. So this minimum delay path, maximum delay path are the exceptions from the standard data paths. Standard data paths will have one clock cycle. Multi-cycle paths means more than one clock cycle, and they will be integral multiples of the clock period. But this minimum and maximum delay path do not fall under that category. They will not be necessarily integral multiples of the clock period. There could be very exceptional cases where they could be like this, like 4 or 2.5, 2.2 nanosecond or 0.2 nanosecond, depending upon their requirement. So those paths we call them as minimum or maximum delay paths. Okay, so all of these concepts which we studied now, we will be declaring them as constraints using commands in the SDC constraints. In the synopsis design constraints, we will do all of this. We will use commands, SDC commands, to declare all of these paths. So for false path, the command is set false path, set multi-cycle path. So like this, we have commands. And by using those commands, we will be setting them in the SDC file. Okay. So here I have given some examples for false path and multi-cycle path, just some commands. To set max delay, set min delay. This is how you will set the maximum and minimum path delays in the SDC file. Set multi-cycle path is the command to set the multi-cycle path. Here also I have given an example for false path. Let me zoom it. Now here, see there's a multiplexer here. And if this input is selected by the select pin, then what does it mean? The data is being transferred from this input pin to the output pin of the multiplexer. So if data is going to be sent from one to output, then the other two paths can be set as false paths because there is no data transfer happening here. Because they are mutually exclusive, right? In a multiplexer, if input is going to be sent through 0, one will be from one, data will not be sent. So if data is being sent from one, this path will be set as a false path, and this select pin path will also be set as a false path, because in these two paths we are not going to use them to send the data. Only this path we are going to use to send the data. That is why we call these two paths as false paths. This is one command also which I have explained here. So set false path hyphen from -2. So hyphen from is the option for this command. Here you have to mention from which pin to which pin you have to set as a false path. So if you do this, then that particular part of the timing path alone will be set as a false path. Next is multi-cycle path. Now to explain this multi-cycle path, so here from flip-flop 4 to flip-flop 5, see they have mentioned, it is a slow logic. Slow logic means what? More combinational cells are there. So here if there are 10 cells, here if there are 10 cells, here 10, and here if there are like 30 or 40, then the data transfer is going to be slow in this timing path, and one clock period will not be enough. So we will use this command set multi-cycle path to set how many clock cycles they require. So here if it is mentioned as 2, which means what? 2 clock cycles are assigned, and the setup check will be done at the second rising edge, because setup check will be always done at the rising edge. For a normal standard clock path, the setup check will be done at the next rising edge. So if the data is launched here, the setup check will be done at the next rising edge of the capture clock path. This is the normal scenario. But for multi-cycle path, what is the scenario? We are using 2 clock cycles. So if data is launched here, the setup check will be here. So you have to mention at which edge you are going to do the setup. So that is why we have mentioned hyphen setup, and then hyphen from which point, from which cell to which cell. This is how you have to mention in the SDC constraint. All right. This I have explained. Now I will come to this setup and hold time concept for formulas for the different types of timing paths. Reg-to-reg, In-to-reg, Reg-to-out and In-to-out. So after this, I'll move to the next part of STA. So everybody is clear with setup and hold time concept, right? What is setup time? What is hold time?
Yes.
All right. So now, before going to the 4 different types of formulas, we need to understand these 2 concepts, which is called as required time and arrival time. Required time, arrival time. Required time means the time taken by the clock or the time which you are assigning. Arrival time means the data path time. Let me write it there. Required time is the clock path time. Arrival time is the data path time. Okay. You have to remember this for all the formulas. This will be the same. And for setup and hold, we have 2 concepts, setup slack and hold slack. So for setup slack, required time must be more than the arrival time. Required time must be more than the arrival time. And for hold slack, arrival time must be more than the required time. Why we are having this? Because what is setup time? The data must be stable before the active edge of the clock. So the data must arrive early than the clock. So if the clock is arriving at 1 nanosecond, the data must arrive before 1 nanosecond, anytime before 1 nanosecond, 0.9 or 0.8, depending upon the setup time. So if setup time is 0.1 nanosecond and clock is arriving at 1 nanosecond, what time the data must arrive? At 1 nanosecond, clock is arriving, rising edge of the clock. According to setup time definition, the data must arrive early, which means the data must arrive before the clock has arrived. So the data must arrive somewhere here. So before this part, somewhere here, the data must arrive. And the setup time is 0.1 nanosecond. This is the setup time. So now tell me at what point the data must arrive so that it is going to reach before the setup time.
Less than 0.1 nanoseconds.
Not less than, yeah, less than 0.1. So how would you say in terms of 1 nanosecond? At 0.9, any time before 0.9 nanoseconds, the data must arrive. 1 nanosecond minus 0.1. So any time before 0.19 nanoseconds, if the data arrives, it is going to be stable. If it is going to arrive at 0.95 nanoseconds, will it be stable? 0.95 nanoseconds means what? Data is going to arrive somewhere at here. It means what? There is a violation. The data must arrive before the setup time. So the data, if the data must be stable, it must arrive either at exactly 0.9 nanoseconds or before 0.9 nanoseconds, not after 0.9 nanosecond. Is this concept clear?
Yes.
Any other is anybody else having any doubts in this setup time concept? Because only if we understand setup and hold, we can understand entire STA.
Can you explain it once more?
Okay. Okay, I will give you a real-time example. See, assume there is a bus which you have to board at 9 p.m. from Bangalore to Hyderabad. All right. At 9 p.m., the bus is going to start. But you are getting a message saying that you all have to reach at 8:45 p.m. itself. Because from 8:45 p.m. to 9 p.m., they are going to do all of those background checks, like checking your Aadhaar card, checking your seat number, number of passengers, arranging your luggages. All of these works they are going to do in that 15 minutes from 8:45 to 9. All right. So this 8:45 to 9 p.m. is what? The setup time. And at 9 p.m., you come or not, the bus will start. The bus is not going to wait. If the passengers arrive or not, the bus is going to start at 9 p.m. So in this case, the passengers are the data and the bus is the clock. So if the clock or the bus is going to start at 9 p.m., only if you reach before 8:45, the conductor or the driver is going to do all of those checking in that 15 minutes, and you can go and settle easily on your on your respective seats, and at 9 p.m. the bus can start at the exact designated time. So this is the same for flip-flops. The flip-flop is going to carry the data which is going to be sent from any input port or from any combinational cell, and this flip-flop is going to process the data. So for it to process the data, the data must be stable even before it is going to process the data. So the data processing is going to start at which point? At the clock rising edge. So at the clock rising edge, if it is going to process the data which must arrive must be stable even before the clock rising edge. So for that, we have a disciplined value which is called as setup time. So this setup time is this 0.1 nanosecond. So the data must arrive at what time? At 0.9 nanosecond or before 0.9 nanosecond, not after 0.9 nanosecond. If it is going to arrive after 0.9 nanosecond, the flip-flop will not be able to process it properly and there will be some stability issues. You got the point?
Yes, yes.
So next is hold time. Hold time means what? The data must be stable after the arrival, after it has reached the flip-flop. Because the flip-flop is going to process the data and then it has to safely transfer it to the queue pin. Now, if we are going to consider the same real-time example, after you have boarded the bus also, all the passengers must be seated in their same designated places. Now, instead of sitting in their designated places, if everybody is moving around or if everybody is moving towards the left side of the bus, what will happen? The driver will not be able to drive properly because the load is not distributed equally. If every passenger is moving here and there, running around, he will not be able to do his job properly. His job is to take all of the passengers safely and also at the same time. If it is mentioned that next day by 2 a.m. they are going to drop at Hyderabad, he has to do that and also he has to carry the passengers safely. So likewise, the flip-flop must transfer the data to queue pin at the designated time and also the data must be stable. So for the flip-flop to be stable, to process the data, first the data must be stable. So that data stability which we are going to check within the flip-flop is the hold time. So the data must be stable for some time after the rising edge also. So this is called as hold time. We call it as T hold, TH. So for some time after the rising edge, the data must be stable. So that sometime is the time where the data is going to tap the input which it received at D to Q. So after the data has reached Q, there is no need for that to check for the data stability because it already reached safely to the Q point. So for T hold, arrival time must be more than the required time. So here the rising edge is 1 nanosecond. Now the data has already entered the flip-flop. So it is practical only to check after the data has arrived the flip-flop. So here if this hold time is 0.1 nanosecond, which means what? The data must be stable from 0.9 to 1.1 nanosecond to satisfy both setup and hold. To satisfy only setup, it must be stable before 0.9. To satisfy only hold, it must be stable from 1 to 1.1 nanosecond. If we are going to consider both the setup and hold window together, the data must be stable till 1.1 nanosecond. So that it will, setup will also be checked, hold will also be checked. Shall I move to the next slide?
Yes.
So we'll see the formulas quickly for Reg-to-reg. You have a register. So this is the launch register. We call it as the launch flip-flop. And this is the capture flip-flop. And there is a combinational delay. Combinational delay means the gates and plus wire delay because we obviously use wires to connect them, right? The nets will also have their own net delay because of resistance and capacitance attached with each metal wire. So these nets will also have delays. These cells will also have delays. So the combination, so those delays are collectively called as combinational delays. So for Reg-to-reg, the required time is, so what did I say in the previous slide? Required time is the clock path time. So all the delays with respect to clock path, we will be mentioning in the required time column. The required time means what? Clock period minus the setup time. So just like how we saw here, the clock period is 1 nanosecond and the setup time is 0.1 nanosecond. What is our requirement? The data must be stable even before the setup time. So clock period minus setup time is the formula for required time of Reg-to-reg path. Okay. Next is arrival time means what? The time taken by the data to actually travel. So how the data is traveling, you see the diagram and then see the formula. Then only it will be easy for you to understand. When the clock is enabled, as in at the rising edge of the clock, the data is moving from the clock pin to the Q pin. So we saw this clock to Q delay, right, in the previous slide. So we have to consider this clock to Q delay also. Clock to Q delay means what? The time taken by the flip-flop to process the data. We have to consider that. So that clock to Q delay of the flip-flop, which is mentioned here, plus then it is moving through this combinational delay. So it could be some hundreds of picosecond or ns depending upon the cell delay of each of the cell. So those delays we have to consider. Combinational delay, which is sum of gate delay and the wire delay. And finally, it is reaching the D pin here. So since our data is traveling through these elements, we are going to consider the delay of those elements. And those delays will be called as arrival time. This is the formula for setup time requirement of reg-to-reg path. Required time minus arrival time. All right. Next is hold time. For hold time, we will not consider the clock period because the data has already reached, it has already entered the flip-flop. The hold time is only that 0.1 nanosecond after 1 nanosecond. So here, the required time is only the hold time. And the arrival time is the same because the data is going to follow the same path only. It is not going to take any other path. So the arrival time is going to be the same. Only the required time will change, which is the hold time. So arrival time minus required time will be the formula for hold violation. Okay, so this is the formula for setup and hold time for the reg-to-reg path. Now in the next slide, you can see how it is changing for in-to-reg path. Now you see this diagram, this is the input port. From this input port, the data is being sent to this flip-flop, right? Now this input port, this is one block and there is one more block. This one more block is handled by one more PD engineer and the data is coming to this input port from a register from a block which is outside this blue block. So if this block, we are handling this block, we have to know with how much delay the data is coming to the input port. Because obviously from a register only it is going to come. So now here the required time is the same. For the setup, it is the same clock period minus the setup time. But the arrival time, you have to consider the clock to queue delay of this register plus the combinational delay if there is any, plus the combinational delay of the delay which of the cells which are present in our block will be the arrival time. So arrival time means the time taken by the data to travel. So we have to consider through which elements our data has traveled. So our data has emerged from this register. It has moved to some combinational elements and then it has moved to some other combination elements through the input ports. So we have to consider the propagation delay of all the elements through which our data has traveled. So that is why the arrival time will be clock to queue delay of the register 1 plus the combinational delay of this block plus the combinational delay of our block. All right. And for in-to-reg, required time will be the same. Again, for hold time, we will not consider clock path, clock period, only hold time. So hold time of this register because we are interested about in-to-reg path of this particular register. So the hold time of this register and the arrival time will be the same. Clock to queue delay plus combinational delay. So in this case, the clock to queue delay is the same. The same. R1 plus combinational delay 1 plus combinational delay 2. Okay. This is how the setup and hold equations will slightly vary for in-to-reg paths. Next is reg-to-out path.
No.
Now, yes.
Can you please just walk through the reg-to-reg path once?
Okay. Reg-to-reg path. Are you clear with the
Yeah, this is
required type?
yeah, kind of. And that's why I just want I'm having
Oh.
some confusion about that.
Okay. See, required time means the path the clock is taking. Arrival time means the path the data is taking. Is it clear? This part,
Yeah.
is it clear
Yes,
for
yes,
you?
yes.
Okay. Now we need to know with how much delay clock is coming, with how much delay data is coming. Correct?
Yes.
Now to know that delay, we need to know through which elements my clock traveled, through which elements my data traveled. Make sense?
Yes.
So for if it is going to if to know that we need to know where my data emerged, what was the start point of my data. from the start point and then through which other elements it traveled to reach the final point. So my data started at this register, correct? When the rising edge of this, at the rising edge of the clock, D is moving to Q. So this is the start point of my data. Is it clear?
Yes, yes, yes.
So the start point is nothing but this flip-flop. Now any cell, it could be a combinational cell or a sequential cell, it has its own propagation delay, right? For,
Yes.
for that particular cell to process the data and push it to the output, it will take some time. If you are sending the data at 1 nanosecond to this flip-flop, for that data to reach Q, it will take 1.1 nanosecond or 1.2 nanosecond. Correct? So we
Yes.
need to consider that delay. So that is this clock to Q delay of this flip-flop. Okay. Now, first element delay we considered. So from here, it has moved here. So what is the next element in its path? Combinational delay. Some gates are there. They have just cumulatively mentioned it as combinational delay. Some gates are there. Now, let us say there is this flip-flop. There is an inverter. There's a buffer. And this final capture flip-flop. If this is taking 1 nanosecond to process the delay, this is taking 0.2. This is taking 0.1 nanosecond. So my data has started from this flip-flop, moved to this inverter, and then moved to the buffer, and then finally it has reached the destination point. So it is reasonable for me to consider the delay of all the elements through which it traveled. So in this case, what is the arrival time?
Yeah, understood. It's first flop delay and then next combinational delay, and at the point where the input to
Yes.
the
So 1 nanosecond plus 0.2 plus 0.1, 1.3 nanoseconds of time my data has taken to reach this capture flip-flop from this launch flip-flop. That is the arrival time. Still not clear?
The first one I was thinking that required time is there, right? Clock period minus setup time. That's just I was trying to process it out.
Okay.
Rest all are clear.
Okay. So what is our setup requirement? There is the clock signal. This is the clock I'm talking about. There is the data. And this data must be stable before the setup time.
Correct.
Okay, this is the requirement. Now, data, this arrival time you understood, right?
Yes.
This part. Now,
Yes.
for this clock also, this clock is also going to start at some point and end at the clock pin of this flip-flop. So there is a clock port here. Now the this clock signal will also take some time to start from this clock point and reach this clock pin.
Yes.
Correct?
Yes.
So so I am considering the entire clock period. So which is 1 nanosecond. And the setup time of this flip-flop is 0.1 nanosecond.
Yes. Understood.
So the required time for the data to be stable is 1 nanosecond minus 0.1 nanosecond.
Correct.
So the required time is required time is 1 ns minus 0.1 ns, which is 0.9 ns. Now arrival time, clock to queue delay. So let us say it is some 100 ps, or in terms of ns only, I will say 0.1 ns plus for an AND, there is an AND gate, it could be 0.2 ns plus a buffer 0.3 ns. What is the sum? 3, 4, 5, 6. So 0.6 ns time the data has taken to reach the capture flip-flop from the launch flip-flop. Now, what is the setup formula? Required time minus arrival time, right? RT minus AT. This means 0.9 minus 0.6, which is 0.3 ns. So what does this mean? The data must be stable before 0.9 ns. So by this, what we are concluding, our data has reached at 0.3 ns itself. So there is no setup violation.
Yeah.
We want the data to come only at 0.9, but our data is very good. We need the data to come here, but the data has arrived at 0.3 ns itself, and it is also stable. So there will be no setup violation. Data has arrived at this point itself. Now, if the data has arrived at this point, which means what? There is a setup violation, and the data will not be stable. So this is what static timing analysis will do. Now, here I have taken an example of one timing path. In real-time scenario, we'll be having millions of timing paths. So it is not possible for us to do this analysis for all these millions of timing paths manually. So we will give all of the inputs required for the PrimeTime or the Tempest tool to do this STA, and we will feed all of these information, and the STA, the tool will run and check if all of those millions of timing paths are clearing setup violations and hold violations or not. We will get those reports only at the end of STA. This is what STA is going to do. So this setup check is one of an STA check. So just like setup check, we will do hold check. And then there are some other checks called as min pulse width violations, clock gating checks, clock gating setup check, clock gating hold check, recovery time, removal time, like this multiple checks it will do. And it will give us the reports. That is what STA is all about. We will include that here. I haven't included. So setup checks, hold checks, clock gating setup and hold checks, min pulse width violations, DRV checks, so DRV checks means max tran, max cap, and max fan out checks. So as we are having millions of timing, not millions, at least thousands of timing paths in our design. And for all of these timing paths, we need to run these checks. So if our timing paths fulfill these checks only, means our design is constrained. Else we have to redo the design. we have to do some optimizations in the placement stage or in the routing stage or in the floor plan stage itself to fix those timing violations. This STA, what it will do, it will check all of these checks for all the timing parts in our design, and it will give us a report where it will state if the timing parts have met the setup or hold violations or it has violated them. That only will be dumped as a report at the end of STA. You got the point of what STA will do? So the setup check is one of the check that an STA tool will do. Shall I move to the next slide, In-to-reg path?
Yes, please.
Any doubts you can ask me? All right. If not, I'll move to the next slide. So next is In-to-reg path. See, now the tool will do all of these. There is no need for us to feed all of these formulas, but as engineers, we have to understand, right? So that's why I'm explaining all of this. So next is In-to-reg. So for In-to-reg, again, see the required time and arrival time concept is the same. Required time means what? The path taken by the clock. Arrival time means the path taken by the data. So in that path, which all elements it has crossed, we need to calculate the delay of those elements, add it and put it in the formula. Required time minus arrival time for setup, arrival time minus required time for hold, and then we have to check if it is passed or not. So if the value is positive, it means it has passed the setup check. If it is negative, it means it has violated. Okay. So for In-to-reg, required time is the same. Clock period minus setup time. Arrival time means what? From where the data has emerged and then what all elements it has crossed to reach the final point. So in In-to-reg path, technically the data starts from a register which is present in some other block of the IC. So we have to consider that delay also. So the data is starting from this register. So the clock to queue delay of register 1, and then if there is any combinational delay, that delay, and then the combination delay 2, and then the final point is the deepen of this register. So all of these delays will comprise the arrival time of In-to-reg. And the required time is for In-to-reg for hold is only the hold time, and the arrival time is also the same. So I will change it. So here it is the same. Arrival time is also the same. Yep. Next is Reg-to-out. Again for Reg-to-out. Now here, can anybody tell me why the setup time is not present here? In these two formulas for Reg-to-out and In-to-reg, the required time was clock period minus the setup time. Clock period minus setup time. But for register to output paths, required time, we are not having setup time. Can anybody think of why we are not having a setup time here? Can anybody think of why there's no setup time?
I think because we calculate setup at the launch edge and hold is calculated at capture edge. So
Mhm.
that's why.
Setup and hold are with respect to the capture flip-flop only. But here we don't have a flip-flop to capture. What is the endpoint here? It's just an output port. Data is starting from a register and is ending at an output port. It is just a port which is going to
transmit the signal to any other element which is after the output port. An output port does not have a setup time. Setup time is only for flip-flops because they are sequential elements and we have setup and hold times for flip-flops. Ports do not have any setup or hold time. You got the point? These ports are not going to process the data. They're just going to transmit the data. Just wires, that's all. So these wires merely don't have any setup or hold time. That is why required time is only the clock period. Did you guys understand this concept? Here there is a register, and this register, from here the data is going to emerge. It is going to go through this combinational logic and end at an output port. What is the functionality of this output port? It is just a pin which is going to take the data from this combinational logic and is going to connect it to the combinational logic. It is just doing a connection work. That's all. It is not doing any processing there. So there is no need for us for a setup or hold time for input or output ports. That is why there is no setup time for the required time for Reg-to-out. It might look a little dizzy now because if you are introduced to these concepts, if this is the first time, it might be confusing, but as you keep revising the concepts, you'll get the picture. So that is the reason we don't have a setup time for Reg-to-out paths. Okay. Next is the arrival time. Now the arrival time, clock to queue delay of register 1, because we need to know from where the data is emerging. The data is emerging from a register. So the clock to queue delay of that register must be considered, plus the combinational delay, plus the output delay. So the data is reaching this register to, the data is reaching this output port from this register, and from this output port, it is going to be connected to a register. So this combinational delay also must be considered, and that's why it is called as output delay 1, because this combinational delay is going to be the combinational delay of another block. That is why the output delay of this block is also considered for the arrival time of Reg-to-out paths. Next, when coming to the hold requirement of Reg-to-out paths, only hold time of this particular register. Then the arrival time is again the same. Clock to queue delay plus the combinational delay plus the output delay 2. This output delay 2 is nothing but the combinational delay of the other combinational delay which is present in the other block. Here also I have mentioned output delay 2 is the combinational delay minus the hold time of the register. All right. So next I will so these are the formulas for Reg-to-reg, In-to-reg, Reg-to-out and In-to-out. So for In-to-out setup requirement, we will not have any flip-flops in between. We'll be only having combinational delays. So the combinational paths have no clock defined because clock periods are only for sequential elements. So we will consider only the cell delay and the respective net delay for the in-to-out paths. Use a virtual clock or set path delays to construct the input to output ports. Now this is a tricky concept. Let me explain. Now what they have mentioned here, in an input to output port, here in the first example, if you see, which I have mentioned here, from this input port to the output port, first thing is we do not have any registers. We will only have combinational paths, combinational logics, gates and
buffers inverters. Only this will be present in an input output port. But this input port might get data from a register which is outside our block. And this output port will send data to a register outside our block. And that register will be driven by a clock, correct? So we have to mention the clock period of that register using a command called as virtual clock for In-to-reg parts alone. Use a virtual clock or set path delays to construct the input and output paths. So the command is set virtual clock. So again, this is an SDC command, which we will be using for constructing the input output requirements in the SDC file. Is this virtual clock concept clear? Shall I explain again?
Yes, ma'am. I'm a little confused.
Yes, sure. See, for the other parts, In-to-reg, Reg-to-reg, Reg-to-out, all of these three parts are involving registers, and these registers are driven by clocks, correct? We do not have any registers in between, but the data which is coming to the input port will definitely be driven by a register which is outside the block. Is it clear till now? The data which is entering this input port will definitely be from a register. Here, just like this In-to-reg, which I explained here. Now here, this input port, data is entering to this block through this input port. But where the data is originating from a register. Clear till now?
Yeah.
But in input into outputs, we do not have any registers involved directly. We have registers involved indirectly, because we are not considering the timing path from this register. We are considering the timing path from this input port, but indirectly the data is coming to this input port through this register only. The data is not coming from anywhere else. The data will originate only from a register. So, since this register is indirectly involved in an in-to-out path, we have to mention the clock period of this register. Now, to do that, we will introduce an exclusive command called as set virtual clock. So in this virtual clock command, we will set the clock period of this clock which is driving this register, and that value will be used to calculate the delay of the data which is arriving at this input port. Where have I explained it? Here. Now, let me write it down. So there is a In-to-reg path. Okay. So this input port is in one. Okay, this is the name of the input port, and the name of this register is sorry, into out, right? Yeah. So output port is
Now we are going to, we are only bothered about the data which is transferred from in1 to out1. But we all know data will originate only from a register. Keep this in mind, data originates only from a register and not from a clock port or not from a combinational path. When we are doing static timing analysis, we consider register only as a originating point for a data. Now that is the basic which you have to remember. Okay, but for into out path, we don't have any registers involved directly. We have registers involved indirectly because the data which is coming to this input in one port has originated from the register which is somewhere outside in the block. So we have to consider the clock period of the clock which is driving that register. So that clock we will mention using a command called as set virtual clock. We will get the clock period of that clock and mention it here as hyphen period 1ns and then hyphen waveform. Then the normal options which we use, so 0 to 5, and then name of the clock is, I will set it as virtual clock. So this is how in the SDC I will write. And the functionality of this how this virtual clock is attached to this into out path will be mentioned in the RTL. So this you don't have to worry. You have to worry only about the SDC. So when we are writing an into out constraint in the SDC, for into out alone, we have to mention a virtual clock. And this virtual clock period is the period of the register through which the data is originating, and that data is only going to reach the in one port. So we have to consider the clock period of that particular register for calculating the setup and hold violations of an into out path. So we are using this command called as set virtual clock. Why we are calling this as a virtual clock? Because this clock is indirectly involved in this data, in this timing path. It is not directly involved in this timing path. It is indirectly involved. So that is why we call it as a virtual clock. Make sense?
Yes.
If you are having any user guides or PrimeTime user guides, it will, if you keep reading it and if you keep going through these concepts again, it will be even more clear. There is a clock involved in into-out path, but it is involved indirectly. So we have to consider that delay also. So to consider that delay, we are using this virtual clock concept to involve that delay in the into-out calculations. Only then it will be accurate, or else it won't be accurate. That is why we are using this virtual clock concept for into-out paths alone. Okay. Next is, yeah, so this one I will come later. So this is the script, a sample script, a sample STA script. So this STA we can run in any tool, PT tool or Tempest tool, any tool we will read. Now here I have given the commands. So read libraries. So first is we will read all the input like the logical libraries and logical libraries or the timing libraries of our design. We will read it using read underscore lib command, and then we will read the netlist of our design using read underscore verilog, and then the set top module. So the set top module command is used to set the design name. So every design will have its own top design name. So that design name we have to set. And then two other input files which we have to read is the spec file and the SDC file. So this SDC file only will have all the data which we discussed earlier. The setup time, hold time, these multi-cycle paths, false paths,
all of those data will be in the SDC file. And the SPEF file will have the extracted parasitic and capacitance values which were extracted from the routing database. So after routing is done, we will extract a file called as SPEF file, which is standard parasitic exchange format file, which will have the actual resistance and capacitance values of our design. So that file also we have to read, SDC file we have to read, and then we have to do some settings. And these settings differ according to our design's requirements. But I have included the basic settings which we have to do for an STA. First is set delay calculation mode, SI aware true. SI means signal integrity. So when we are going to do the delay calculation for our design, we have to consider the factors which are causing the delay. So that extra factor is this signal integrity factor. So the signal integrity means what? When there are any crosstalk issues which we are seeing in our design, we will see delay because of the crosstalk also. So apart from the cell delays and net delays, which we are considering for in the setup and hold equations, we have to consider the delay because of the crosstalk also. So we have to mention the tool, mention to the tool that include the crosstalk delay effects also. Only then we will be getting an accurate timing analysis. So using this command, I am making sure that crosstalk delay effects are also considered. And then set SI mode enable delay report true. So this will give a report with the crosstalk delay parameters in the report. And then glitch analysis. Glitch analysis means noise analysis we have to do in the STA. So to do that to do the noise analysis, we have to add two commands, which is set SI mode. SI means signal integrity mode. Enable glitch report true and enable glitch propagation true. These two settings we have to make. And then finally, update timing. So this update timing command will do the timing analysis with all of these settings which we have enabled. And then finally, report timing command. This command you must be aware of this report timing command. And this report noise will give the crosstalk effects in our design. So this is how our STA we will be running in the STA tool. The basic script with which we have to run the STA. And here I have included a example of a timing report. So path, this is one example how a timing report of an after an STA will look like. So first path, see in the first path itself, it has mentioned that this particular path has violated the setup check. And it has done the setup check at a pin Reg-12 clock. So there are 12 registers, and for the 12th register at the clock pin, CK means CK pin of this register. So when it has done a setup check for this register at the CK pin, the setup has been failed. So the end point is the D pin of this register. Begin point is the Q pin of Reg 0. So our data path has started at the register 0. This is Reg 0. And it has ended at Reg 12, B pin. And the path group means it to which clock it belongs. So it belongs to a clock M_RCC_clock. So this timing path belongs to the clock period of this clock. And then analysis view. This analysis view is taken from the MMMC file. So there will be multiple analysis, right? Multi-mode, multi-caller. So there will be multiple analysis views with respect to the mode and caller combinations. So that analysis view will be mentioned. And here the tabulation is mentioned. The required time is 20.183. So whichever calculation was done for this particular path, the required time is mentioned. Arrival time is 20.240 and the slack is required time minus arrival time. So 20.183 minus 20.240 is minus 0.057. So which means what? The setup calculation has failed for this particular path. The data has arrived late. So after the setup time only this data has arrived. So setup violation has happened in this particular timing path. Now after analyzing this, we have to highlight this particular timing path in the Innovus database, analyze what combinational elements are present, what is the cell delay of each of those elements, if there is any detours, or if the net length is more in this path. We have to analyze all of these reasons, and then we have to do the fixing. If we can swap the cells, or if we can do, if we can insert any buffers, or if there are any extra buffers, we have to remove them, because buffers are just going to improve the signal strength. And if the drive strength is more of the buffer, then the delay of the cell will also be more. So in the place of a 1x drive strength buffer, if there is a 4x drive strength buffer, it is not required. So if we are going to replace that 4x drive strength buffer is with the 1x drive strength buffer, then the cell delay will also reduce, which means the arrival time will reduce. And finally, required time minus arrival time, we will get a positive slack number. So this is how you have to do the analysis and do the fixing. So STA will not do the fixing. It will only do the analysis and give us the reports. We have to analyze those reports and make changes in the PNR database. And again, we have to do an STA until all the paths are passing. Any doubts so far?
Actually, while writing the script for STA, the input you have is the netlist diagram, or
Netlist, the routed netlist, the final netlist which we obtain
okay,
after routing. That will be the input.
okay, okay.
Any doubts in STA which we discussed so far? Basically, in static timing analysis, we will run a number of timing checks, which are the setup checks, hold checks, clock pulse width violation checks, clock gating checks. And we are going to do all of these checks using a particular STA tool. So the tool will do all of these checks for all the timing parts in our design, and it will give us a report. If there are any violating parts, we have to analyze why it is violating, and we have to make those changes in the placement and routing database. Again, we have to take the new database to the STA tool, run STA until all the parts are passing. Even if some 10 or 20 parts are passing, we can try to do some manual fixes. If 100 and 200 parts are failing, again, we have to keep running the STA until we get all the parts as passed. So this is with respect to Tempest. These commands are with respect to Tempest. With respect to PrimeTime, it will slightly vary. Just there won't be much drastic changes in the commands. There will be very slight variations in the command formats. That's all. But this is the script which will be followed this until this. Any doubts? I hope you guys are aware of DRV checks, right? Max tran, max cap, and max fan out checks. Max tran means the transition time for a cell which we have set in the SDC must not be violated. So if we have set 100 PS as the transition time for a particular cell, that cell must not take more than 100 PS for the transition, which means for the input transition. If the cell is taking 100 PS to do a transition from 0 to 1, and I have mentioned in the SDC that this particular cell must only take 100 PS. After doing the PNR, if I'm going to do a DRV check, it must be less than 100 or equal to 100. It must not take more than 100 PS. If it is taking more than 100 PS time for transition, it is a transition violation. Next is capacitance and fan out are with respect to the load of the particular cell. So this capacitance value, I will mention this also in the SDC in terms of farads. So this particular cell can only withstand 15 picofarads of load. But after doing the PNR, if the in-house engine is assigning more load, more than 15 picofarads, then it is a capacitance violation. And fan out is also load, but in the number of cells which are attached. This is a cell. And if for this cell in the SDC, if I'm mentioning 3 fan out, which means what? Only 3 cells can derive output from this cell. After PNR, if the in-house engine or if the FC engine is attaching more fan outs, like 4 or 5, then it is a violation. That has to be fixed. Next is min pulse width violation means in the clock period, in the clock, when I'm defining the clock, I will mention the pulse width of the clock also. Pulse width means what? The duty cycle of the clock. So 50% half for the for the active high and 50% for the active low. If this is the pulse width I am mentioning in the SDC, now because of the clock propagation, because of the net delay of the clock, this time might reduce because of the transition time taken more by the clock. So this 50% will keep reducing to 40%, 45%, 30%, and it will finally reduce like this. So active high will be 30% and active low will be 70%. So what will happen because of this? Now, if I am assigning rising edge of the clock to a flip-flop, which means what? 50% of the clock period. So if the clock period is 1 nanosecond, 50% means 0.5 nanoseconds of clock period I am assigning for the data to travel. Now, because of this pulse width violation, finally this 50% has reduced to 30%. So 30% means what? 30% of 1 nanosecond means 0.3 nanoseconds. So the clock is only allowing the data will be allowed to travel only for 0.3 nanoseconds, but the actual time is 0.5 nanoseconds. So because of some clock transition violations, the pulse width has reduced to 0.3 nanoseconds from 0.5 nanoseconds. So what does this mean? The amount of time allowed for the data to travel is reducing because clock is the master, correct? Only for this active high, the data transmission will happen. So from 0.5 to 0.3, if the clock width is reducing, it means that I am reducing the data for, I'm reducing the time which is allowed for the data to travel. So because of this pulse width violations, we are constraining more on the time allowed for the data. So this will also create setup and hold violations. So to avoid that, we have to do these min pulse width violation checks to first check if this violation is happening or not. If this violation is happening, again, we have a lot of fixes like inverter tree, buffer tree fixes like that. We have multiple fixes to fix this clock pulse width violations. So STA tool will run these checks also and it will give us a report of this pulse width violations. If it is occurring, again make the respective changes in the PNR database, do the STA again, check the reports. If it is passing, no problem, we can send it to sign off. Else, again you have to do PNR and do an STA again until all the parts are passing. This is the process of STA. Any doubts?
Yeah, actually, our flip flops are edge triggered only, right? So how the width on width related to the time of data transfer, because the data is transferred only during the edges of the clock, right?
Yeah.
So
At this
how?
edge, the data.
Yeah. So the transfer will happen once it deducts the edge. So it doesn't depends on how much duration the clock is on, right? So how come the pulse width contribute to the amount of data transfer?
It depends on the rising edge. Now this rising edge here, it is happening at 0.5. So this, okay, 0.5. At this rising edge, data transfer happens. And the next data transfer happens here at the next rising edge. Correct? Now this
Okay,
much
yeah.
time is allowed for the data for the transfer to happen. Data transfer starts at the rising edge and it stops at the next negative edge, at the falling edge. Now this falling edge is happening very soon here.
Okay, I got it.
The falling edge, which is supposed to happen at 0.5, is happening at 0.3 itself. You got the point?
Oh, yeah, I got it.
Okay. Any other doubts? Yeah, I will share this PPT with the organizer. You can go through them and you can let me know if you're having any doubts later also. All right. Shall I end the session, or if you are having any doubts also, we can discuss.
Ma'am, please share this PDF and also the recording.
Yeah, PDF I will share. Recording, yeah, the organizer will share. PDF I will share it to her, both the recording and the PDF. Maybe if you guys are having a WhatsApp group, she
Yeah,
will
we
share it.
have. Okay.
Okay, yeah.
Thank you. It was a great session.
All right. Thank you. Shall I end the session, or if anybody else wants to, if anybody else is having any doubts also, we can discuss.
I have one doubt.
Yes.
Why a design engineer should know about STA?
Why a design engineer? Design engineer, you mean by design engineer, you mean the RTL design?
Yeah, RTL is an engineer, yeah.
See, because they are deciding the architecture of the entire IC. Now, if you are having a ALU module, for that ALU module, they are going to decide how many sequential and how many combinational elements are going to be present, how many muxes are going to be present. And the clock period is also decided based on the logic depth. So if the RTL which they have given, now let's assume they have designed a module which is doing some functionality, has 5 flip-flops and 10 gates. Now if the same module I am going to, if the same functionality I can obtain with 3 flip-flops and 2 gates, then this will save more amount of clock period, and also there will be very less delay because of these cells involved. And so the possibility of timing violation happening in the first module will be less in the second module because the number of cells involved are less. Does it make sense to you?
Yeah, okay. So like the complexity of the complexity of design is high, there will be a lot of chance for the violations. That's what you are telling.
Exactly. Now, in this digital electronics, which we have studied, if you remember, we have all of these optimization techniques like Boolean optimization, K-map reduction techniques, which is mainly focused on reducing the logic, but to obtain the same functionality.
Yeah.
Where we reduce the number of literals, but obtaining the same functionality. So that is what basically the RTL people do. They do the functionality at also where they will also try to optimize the design so that the timing violations will not also happen in the backend. If I'm having 10 timing paths in my design, and if I am able to achieve the same functionality with 5 timing paths, obviously I will choose the second one. So the RTL people has to focus on reducing the functionality, but not no, reducing the number of timing paths, but not making a compromise on the functionality. And also this STA, see, it is not like how do I tell you? It now this entire IC process, both the front end and the back end people are involved. So every stage of this IC, starting from the RTL design, verification, DFT, synth and PD, every stage has their own optimizations to be done. So if I start a design with a very good floor plan, the congestion number which I will see after routing will be very less compared to a bad floor plan design. So every stage of this of the VLSI cycle from front end till the back end will contribute to the optimizations with respect to timing, power and area. So it is not like only back end people has to focus on this. It has to start right from the front end. Any other doubts? Okay, I will end the session now. I will share the PPT with the organizer. From her, you can get the PPT and the recording also. All right.
Thank you, Christina, for the session. It's a nice session. Thank you.
Thank you. Thank you.